Alright, hell yeah. Now, if I made your day better because I said hell yeah, write in the comments, hell yeah. And you know what? I'll give it a little heart. Now, the writing portion of this, the actual math, that starts at minute 34. But I definitely want to take a moment to talk about how after that, I looked up a fundamental of what we were doing. We were setting up an integral, and we're going to take a slice, so we have some sort of function, and I want to go to where that function is this value, and then take a slice of it. And it only makes sense to me is if I take an actual visual slice, a change in x, a dx, which is a infinitesimally small change in x, makes my head hurt. And so for the first 30 minutes of this, we talk about how we went to Google, and then we kind of work our way through there. But it's just talking, and that could be useful to watch before this, or you could watch the math portion first. Alright, hell yeah. Alright, hell yeah. So this video does have pen and paper, but I'm just doing what I Googled at the end of my session, which is this: how to set up an integral where you use a delta x. If I have a function and I'm going to evaluate that function at some point and then have a significant change, this is what this means, like it's an actual change in x, and then I can make a rectangle, a sliver of area under that curve that's tangible. If I call this dx, that means it's kind of intangible, and I think your mind explodes. You know what I mean? And we could set up the area under the curve as just one change in x, and then we just get the area of a square. We could have two. We could divvy up the area into two little changes in x's. And so, and I just didn't understand how you get from this change in x to where you actually do slice it up into an infinite number of slices. That's where n is infinite. And how that plays out. And it is very associated with the fact that you are finding the area under the curve. You do have limits between a and b. So if my limits are between 0 and 1, that's what we explore in this video, then b is 1, a is 0. And so we have, and then we'd split that up infinite number of times. And then kind of at the end, I say, well, what if I'm trying to find the area under a rectangle from 0 to 2 with a height of 1? Well, then b is 2 and a is 0. And so this would be 2 divided by infinity. And so, and heck yeah. And I think the secret sauce was coming up with this equation for evaluating the function as a series. Because a series of these i's are going to be an integer. If I'm divvying up a rectangle between 0 and 1 into 10 segments, each of those values are going to be 0, evaluating the function at, let's say, 0, 0.1, 0.2, 0.3, 0.4, and so on until 0.9, and then making the slices a change in x of 0.1. But then I didn't understand this jump, how to go from understanding that I can divvy it up, and even that's kind of challenging. But then where does this become just f of x? And I don't even explain it in the video. This is just afterwards having those aha moments. Is if I do have this, we explore the line that's just y is equal to 1, and from and the area under that curve from 0 to 1. So it's literally a square box. But if I start, and then I actually start somewhere in the middle, and I didn't realize, well, you want to start your limit at a. You know what I mean? So x, for the problem that we do in this video, we would want to start our value of x or x naught or x1 at 0, and then take our first slice from 0. And the wild thing is if we take a progressively smaller slice to where we have an infinite number of slices, then our next value, so our first value of x1 is at the function where x is equal to 0, but what's the next value? You know what I mean? If we have delta x be 0.1, our next value is where the function is evaluated at 0.1. But if this delta x, and this is where the mind trip, it's very difficult for me from a logical perspective to think a differential change in x, a dx, isn't, it is and it isn't. It's like infinity is a number and it's not a number. It's actually not a number. A dx is a definite width. It definitely has a width, but it doesn't have a, you know what I mean? That blows my mind. But anyway, and so if we do have a change in x that's so small, infinitesimally small, and we do move from this value of f equals to 0, this is the secret sauce, to the next value of x. That next value of x will be the next value of x, which is, shoot, that's not a very good way to say it, but that becomes this function f of x. This function f of x says that if I could have x equals to 0, I can have that. And what's the next number that I'm going to come to? Well, I could come to 0.1, or I could actually come to 0.01. I could come to 0.001, and that's 10 to the negative 3. I could come to 10 to the negative 5, 10 to the negative 10, 10 to the negative, you know what I mean? So the next point I'm going to come to would be 10 to the negative infinity. But that point exists. You know what I mean? So if I do move a differential distance, I do come to a new point, and that's the most important thing. I do get a new point with a new value. That new point is just represented by this function, and I'm probably kind of saying it wrong, but that's where I think your brain can bleed. If you act, it's like some of those videos where you're just like, look at this number, it's so big, it's gonna stop the universe. You know what I mean? And it's just like, ponder that for a little while. You can't ponder it. I think dx can become that much of a nuisance. But I think that was the secret side. I can't even explain it in words, but hell yeah, I can evaluate the function at f equals to 0, and then I can evaluate that function at the next smallest. I mean, I can't just evaluate it at f equals 0 again. There's going to be no change. But the function does have, the function next to f equals to 0 is a point. And what's the first point you can come to? Well, you can come to an infinitely number of smaller and smaller points. And that's cool, you know what I mean? Because if we do move an infinitesimally small distance, and let's say and that's where you can even always bring this to a tangible. Let's say you thought you were moving the smallest, distance known to fathomable in your brain. That just meant that you sliced between 0 and 1. You made that many slices. You made an infinitely unfathomable or fathomable number of slices. And so those two are directly related. So if you slice it up 10 times, then and your change in x becomes the proportion of those upper and lower limits in proportion to how many times you sliced it. So it works great if you slice between 0 and 1. If I'm finding the area under the curve between 0 and 1, I have 10 slices. Then my change in x is 1/10. If I have an infinite number of slices, my change in x is 1 divided by infinity. And I think it is useful to think of infinity as a number when you're doing that, else your brain's going to explode. Because it's just like, what would be, I don't know, or have another term for just like, what's the biggest number that you could actually write in a very simple, with very few characters. I should probably start doing that, because my change in x is going to be, my n would be that number. my change in x is going to be 0 to 1, 1 minus 0 divided by that huge number. And so, heck yeah. So I have that large number of slices, and then my change in x between an interval of 1 and 0, 0 to 1, is going to be just 1 divided by that huge number. So, cool. But yeah, so I think the kicker is between this f of x of I, which uses a delta x, and then having delta x in that equation go to 0. The limit as delta x goes to 0, then you just get to the next value of that function. So if you evaluate the function of f of x at 0, the next possible value is going to be 0.000000, infinitely number of zeros, and then with a 1 right there. You know what I mean? However you want to think about that. That's where it's just used, and just that is a value though. It's different than 0. It's not just 0 again. It is a different value. So hell yeah. So that's kind of where we go through. Yeah. So this could be part 1 of that video, or I could just have this at the beginning. But I don't know, I think maybe we'll just have this as part 1, because that was a fairly decent explanation. Alright, heck yeah. And I don't mind getting tripped up into the mentalizing some of this stuff, because negative infinity, infinity, those aren't numbers, they're just concepts. But then it requires, when your limit becomes negative infinity or positive infinity, it requires us to jump from actually summations of little things with area to things that actually, like, I don't know, a little sliver of dx width technically doesn't have an area, but it does. That's mind-boggling. You know what I mean? And so, yeah, that's too much to handle. But you do have to have that jump between a delta x, which actually does have area, and then knowing that if you just divvy up that area into a bunch of slices, that you can, find the area under the curve, and just through an integrated process, you can get a function where if you evaluate it at the limits, and that's the fundamental theorem of calculus, is evaluate it at the upper limit and subtract the value at the lower limit, then you effectively get the area under the curve to a degree of 100% precision, just based on the nature of antiderivatives, reflecting that the derivative of that antiderivative represents the change in that function. And the change represents, a small little estimate of where that function is going, saying like, hey, if I'm at this value, I would imagine it's going to be that same value for, you know what I mean? Like if my car's going 60 miles an hour, I would imagine in the next second I'd be still going 60 miles an hour. But in a second, I might be able to ramp it up to 61 miles an hour pretty easily. But how about in the thousandth of a second? Do you think I'm still going 61? Well, now, yeah, I'm probably still going 61, but maybe I'm going just a little bit higher than 61. Okay, change the change in t to 10 to the negative 10, 10 to the negative 12. I do a comedy joke of how I dropped out of school because I was afraid of small numbers. I think we all are. 10 to the negative 12? That's crazy. But if that's going to be my change in time, I'm still going 61 miles an hour. And so that's where your strip comes from. Cool. I went 61 miles an hour for a very, very small portion of an hour. And now I know how much miles I went. I know the distance now, and that's effectively the area under the curve. And but that's still a rough estimate. But through a mathematical equation, I can actually get the actual, mileage that I'm going. And so the mathematics of finding an antiderivative are 100%, where the only way that I feel that you're gonna, have a tangible and going forward when setting up integrals, is to actually use a change in x. Because if your change in x is just a over b and you have one interval, I think that's the simplest thing to do, especially for physics problems, especially for even work physics problems where you have a force over a distance, especially where the force is greatest at the beginning and then maybe tapers to zero linearly like a spring. I mean, it's not a bad estimate just to assume that that force is the greatest number right at the beginning and stays the greatest number. You know what I mean? Cool. And that's if the force is zero at the beginning and over a distance, that's kind of nonsensical. But, if you pull on a spring, it's going to have a max force right at the beginning. And then as it goes to its neutral position, the force goes to zero. But still, you could just say, hey, not a bad estimate just to say that's the max force. And it's going to be over that distance. So the area under that curve is just a square. And all you're doing there is just saying, hey, my interval is going to be b minus a divided by 1. I'm going to segment this up as one summation. And so now I don't mind putting this, the nuts and bolts. And maybe at the beginning of this, I'll say, hey, if you just want to get to the paper part, because this was the after the fact part. This was going through, exploration, paper and pen, and then looking up a precise definition. And then being like, okay, now I'm solid on this because I'm actually going to experiment with values. And I can, divvy this up. Like we said, what's a big number? I don't know what the biggest number I know is. I'm just going to say 10 to the 6 sometimes gets it done. You know what I mean? A million sometimes gets it. 10 to the 12, that's plenty big for me. I was just saying for physics problems when it comes to time, because if I had 10 to the 12, I'm going to divvy this up into 10 to the 12 slices. If I have this 10 to the 6, that's a million different slices. I don't need a millionth of a second. If I'm doing something in physics that's between 0 and 1 second, like driving, I'm just going to use a thousandth of a second because I can even set that up in Excel and sort through all that data, and it's not too big of a deal. And then so for there, my big number is 1,000. So even right here, for some problems, n is equal to 1,000. Good enough. And I think that's really useful because it's unfathomable to put infinity here, because even the largest number that you know, and then you put infinity, and that's where that's where your brain blows up. You're just like, you can't even fathom it, even though we just use the concept, very loosely or very strategically in a very mathematical way. Hell yeah. But that's where we jump from this summation sign to this integral sign. And then that's the biggest issue with learning calculus, is then we just use an equation that's 100% correct based on mathematical manipulation of finding an antiderivative, where the derivative of that represents the change at each point, where it's more useful to always set it up as a summation. And like I just said, make your interval just 1. Make it the worst summation. Make it the worst estimate possible. And you might get might be 100%. You know what I mean? If you're finding the area of a square box and you do one summation, which we do in this video, you are 100% correct. If I did the physics problem where the force was greatest at the beginning and then tapers to 0 over a distance of 0 to 1 meters, let's say, then I'm going to be off by a half. Like obviously the average force was 0.5, and if I set up the integral with one iteration where I'm taking the value at x is equal to 0, which is the force of that spring, I'm not calculating the other. I'm only going to do one interval. Then yeah, I'm off by a factor of 2. Who cares? You know what I mean? So you should always, that's the whole point of this video, is to start with the most basic. Because some books are awful. They'll even say that if you're trying to find the area under of a square, you don't. You just multiply base times height. But that's crazy because the setup for the integral is the same. And I think it's even trickier because no one, why we go into this video of y is equal to 1 is the equation. of a slope with 0 slope and a y-intercept of 1. And how if you say y is equal to 1, you don't even think that it's like a function that's has an independent variable of x, where actually you input x for all real numbers and you're still going to get 1. And so that is also what we talk about. I think the thing that we don't talk about, and I'll make a separate video on, is how, well, I went through this part very thoroughly, that this function of xi, and we do in the video show that this xi is a series of numbers. Because if we divvy that section from 0 to 1 up 10 times, I'm going to have 10 values here. I'm going to have x of I, this value is going to be 0, then 0.1, then 0.2, then 0.3. If I was trying to find the area under the curve of something between 0 and 10, and I divvied up 10 times, this value would be 0, 1, 2, 3. And we talk about how summations always start with, typically, and I guess they don't have to. I guess you could probably start with 0. I'll have to Google that. But just in summation land, you always start with 1, and then you do integer changes. So I is equal to 1, then 2, then 3, all the way from 1 to 10 for, that's what we do for our problem. And so, and that's where this is a series. And so it's almost more useful because you learn series where you're using a, n, and that's maybe for a separate video, because I think the summation sign is actually unneededly, well, I think it just needs more explanation. The fact that you have 2 letters here, you have an I value that represents, so x of I could be where I could be 1, I could be 2, I could be 3, and I could be an upper limit n. And so, and then done with summation. N could be, and there can always be an n plus 1. The only time there can't be an n plus 1 is if you put infinity here. But if you put an actual definite number, you could have an n plus 1 in that series. You're just not adding that term. You're only adding the terms between 1 to n. But I represents any one of those terms between 1, 2, 3, ... n minus 1, n. And hell yeah. And why these become themselves, why f of x of I becomes f of x, is because our interval, like we said, gets so small that the next value from 0 is just the next value in this function. And so I think that's a good enough explanation where f of x of I mentally becomes f of x. And then this change in x becomes dx, because that's, when we divide by infinity, we get an infinitesimally small. So I think that's that works out too. So inside this, for our first value, we're just gonna start with a. And I think it's a bummer that I chose a square that started at 0, because I should do this where the square starts at 1 to 2. Because that's a little harder to see that 0 is my a term. And even in the video, I didn't catch that. The video, I just start at some random halfway point and call that x. And I don't realize that if I'm setting the lower limit and the upper limit, that value of x is at the beginning, which is 0. So this would be 0, and then this would be this value. The first value would be 1 for I, and then we'd have the change in x. And if change in x is that dx, where it's 1 minus 0 divided by infinity, that gives me the absolute next point in that equation. And so I'm evaluating that next point at the just the next point. And so and you can't even mentalize in chopping something up infinitely number of times and adding those slices, because every time that you think about it in a tangible way, each tangible slice that you think of could also be divvied up into another, and you can't even say another infinite number of pieces. Just, yeah, that's where infinity just is almost a horrible term. Or it's just very difficult to internalize. All right, hell yeah. So I think that's halfway good enough to see how this inner portion is just the next number, and then this delta x is dx. And those are related, because if you throw any number in, and that's where it's just like I like to think of infinity as a number. So if this is infinity, I'm chopping between 0 and 1 up an infinite number of times, but I'm going to think of infinity as just, well, yeah, that's good. I think there needs to be another term of just like, what's the biggest number you can think of? And then negative infinity, what's the most, I even forget if a negative number is a small number. I think, I don't know. I think, no. 0 is, numbers that approach 0 are the smallest. A large negative number is just a large negative number. What we're interested is in a number that approaches 0. So it'd be like 1 over infinity. And so the two cases you could have would be a square box between 0 and 1 and a rectangular box between 0 and 2. For a box between 0 and 1, let's say infinity for the next rest of this little session is just the largest number you can think of. And so that's where, anyway, hell yeah. That's why I need to think of a large number that we all can agree on that's large enough. Okay, sweet. So infinity is a large number that is actually a definite or a finite number. And so I'm divvying that 0 to 1 up infinite number of times. Each slice, the width is going to be 1 divided by infinity. I think that's the easiest thing to see. But if my width of my rectangle goes from 0 to 2, and I divvy that up an infinite number of times where infinity is a finite number, then the width of those becomes 2 divided by infinity. They're double. The width of those small slices are double the width of the slices between 0 and 1. And that only makes sense as if we use a tangible number here. But that's where the thought experiment is, just pretend infinity is a large number, the largest number you can think of. But that's where the slices from 2, your upper limit being 2, your lower limit being 0, that's going to be 2 divided by infinity, and those slices are twice the thickness. Cool. But just for the problem in general, who cares? Twice the thickness. I'm just going to assume it's the next point in that equation. So the equation starts at 0. The next point is this 2 divided by infinity change, and that's the next point on the graph. And that's where this value of f of xi becomes f of x. And so there is a balance that just makes common sense, where if I have a box that I divvy up 10 times, I'm taking 1/10 of those areas and adding those up 10 times. So my summation is adding up 10 things. My width is 1/10. So yes, and then said if I'm adding up an infinity number of things, my width is 1 divided by infinity. If my limits of integration are 0 to 1. I think the kicker was realizing that if I'm adding up the area under a rectangle from 0 to 2, and then for this thought experiment, infinity is just a large number. So if I'm adding up an infinite number of things, the area of those have a width of 2 divided by infinity. And so I think that's an important connection to make. It is useful to use a square from 0 to 1, but I have to be cautious about that. on two regards. Setting up that square with the lower limit of 0, it's hard to see where you're starting at the a term. And so I should do a very simple, or I should change that to a rectangle from 0 to, I should change this to a rectangle starting at x is equal to 1 and going to x is equal to 3. So it would be an area of 2, starting at a is equal to 1. My upper limit would be 3. If I divvied it up into an infinite number of slices, and what's the largest number I can think of? Let's say 1,000,000. So 1,000,000 is perfect. So if I divvy that rectangle up from 0 to 2 into 1,000,000 slices, and I think that's where I'd want to use the square. Because if I have a square that's 1 by 1 square, if I divvy that up into 1,000,000 slices, the width of the slices are 1 divided by 1,000,000. I think that can be easy to see. I think it's actually, and this happens a lot in engineering, where just doubling something isn't extreme enough to see how the width of these slices are double. So I think I should actually start with a square box and a rectangle that has a width of 5. Because then if I divvy this up into 1,000,000 pieces, each of those slices are 1/1,000,000th. You know what I mean? And then if I divvy this one up into 1,000,000 slices, each one of those slices is 5/1,000,000ths. And I think I don't think you can even intuit that if we divvy it up so much. So if we divvy, so that's where, if I have a square that has a base of 1, that's going to be a width, and a square with a width of 5. If I divvy it up once, this width is 1, that width is 5. If I divvy this one up twice, this width is a half, and this width is 5 halves. If I divvy this one up into 5, this width is 1/5, and this width is 1. Each of those widths are 1. So the widths of these will always be 5 times the widths of those. So if my limits of integration go from 5, 0 to 5, where a is 0 and b is 5, then, and I divvy that up 1,000,000 times, then I'm going to have 5/1,000,000ths, which would be 5 times bigger than divvying up the square 1,000,000 times, which would have widths of each of those strips of 1/1,000,000th. And that's where I think it's still useful to even throw infinity in here and pretend that it's an actual number, because I would have 5 divided by infinity. That's a different number than 1 divided by infinity. But here I would have, and here I would still be summing up 1,000,000 terms. One, I'm just summing up 1,000,000 terms that have a width of 1 divided by infinity. And the other rectangle, I'm summing up 1,000,000 terms that have a width of 5 divided by infinity. The area under that larger rectangle is going to be 5 times the area of that smaller rectangle. All right, hell yeah. So I think I'm done with this video. Thanks for joining me. And we'll put this at the beginning. What the hell. And then you can kind of see the pen and paper. But I will, at the beginning of this, kind of put a timestamp to where the pen and paper begins. Hell yeah. Alright, hell yeah. So one of the viewers wanted me to do composite areas and taking integrals. So you use integrals to find areas under curves. And you can use double integrals to find volumes. You can also use single integrals. You can even take a point and then find the length of a line. I think the simplest place to start is finding areas under the curve. And so, always be willing to go to the simplest example. In one of the textbooks, it says you can't integrate this because, you know what I mean, you would just find, if this was a width of 1 and a height of 1, you wouldn't need to integrate it, but you still could. So that's what we're going to do. We're going to put a y-axis here and an x-axis here. And then we're going to, now we can identify some things. Like this is not a function. It's a vertical line. It would have a slope of infinity. Y is equal to mx plus b would be y is equal to infinity x plus b. And so we can't have that. This is also a vertical line, so this is also not a function. The definition of a function, I'm really getting into going back to the fundamentals, is something that's going to take a series of numbers, and the most common thing to do is have a number line that goes from negative infinity to positive infinity, you know, by increments of 1, and then with any number in between, so this is just all real numbers. And then when we choose one of these numbers into an equation or our function, this is going to be our inputs, and this is the independent variable. Then we get some sort of output. Now, if I put in an input of 1, I might get the number 1. That's what we get right there. We actually output the number 1. And if I put in the number, I'm sorry, the number 1 would be over here, if I'm saying this, but yeah, I'm going to get the number 1. If I put in the number 0.1, let's say this is 0.1, hey, I'm also going to get the number 1. That's my output. If I choose this as my input, x, then my output is also 1. So this right here, this portion right here is a function. Now, we don't have it drawn where it goes from negative infinity to positive infinity, but we could. This would be the equation of a line, y is equal to, and if we start with our general equation, y is equal to mx plus b. It's also good to look at this as y is equal to a1x plus a naught, just because that format you'll use in linear algebra, so you might as well get used to that. But this says this is our slope, and this is where it intersects the y axis. So we have a slope of 0, so this value is going to be 0. We have 0x plus, and it hits the y-axis at 1. And so our equation for this line is just y is equal to, I would even still write it like this, 0x plus 1. Don't get rid of things until you're ready to get rid of them, until it's so obvious that when I see y is equal to 1, I know the slope is 0. You know what I mean? But don't get rid of it. Throw it in there, 0x plus 1. Because the crazy thing is this is a function of x. That means that this is my independent variable, and I'm going to change it. Now, some functions you're going to have go from negative infinity to positive infinity. But let's say this is just a line segment where these are nonsensical values. There's no reason to extend the function here just into the negative, and there's no reason to extend it into past positive 1, because from a physical parameter, like, it's not going to make any sense. Like, that number won't generate. That number will be undefined. I don't know how you say that. Undefined. But hell yeah, this number is going to be undefined if my input's going to be 2, or undefined if my input's going to be negative 1. And so the tricky thing is, if this is the equation of a line that's y is equal to 1, it doesn't look like you can insert a value of x. And so I think that's the secret sauce from this month, is just to be like, hell yeah, if I see this, like I was just like, well, how do you know what I mean? Could I just say this is y is equal to 1, times x naught? Because any value that I put in for x is also going to just make this 1. You know what I mean? But then I was just like, well, it's got to be an equation of a line. So if I'm in this actually works for a lot of cases if you're going to do integration, just to even show that this is a function of x. It's just x to the 0 power. But if we're looking at this as a line, it's just way fundamental to say this is 0x plus 1. It's a slope of 0, and now if I put in any value of x, if I put in that value of x of 1 right here, I'm going to have 0 times 1 plus 1. Well, guess what? That's 1. If I put in an x value of 0, 0 times 0 plus 1. Hey, great, that's 1. And I think it's very valuable to take the simplest, square, and I feel, novel, not genius level, but just novel that I'm, able to see that this could cause confusion down the line when people are just starting, with I need to have like an x squared. I need to have an equation that's y is equal to x. You know what I mean? And then find the area under that. Sweet. All right. All right, hell yeah. So that was way too long of an introduction, but let's try to kind of bust this out. What integration does is says, hey, I'm going to come to any value over here. So I'm going to choose an x value of whatever that is. So that's going to be my chosen x value. And if I choose this x value, it's going to give me a y value. That's going to be that. And then so what I want to do is find a little slice of area. And so I'm going to change the x value. And you could just go right to calling this a dx, which means that it's infinitesimally small, but it's useful to always use this delta x. And I think that's, it's useful to do that, so you can be like, hey, I'm just going to, this is my x, and then I'm going to go change x a little bit, and now I can visually see that that is, well, it's another shape, and it's an area if I say, hey, whatever this value was, which is the y component, and this is also gets confusing, where it's just like if the equation of this is y is equal to 1, or y is even equal to 0x plus 1, y is the output, and we can also write this as, hey, this is a function of x, or we could just say this is y as a function of x is equal to 0x plus 1, or we have a function of x, which is 0x plus 1. And then you could, for this y-axis, you could call it y, you could call it y of x, you could call it, and I don't even know if like that's appropriate. I think it is. I think you can either call it y, you can call it y of x, and you can call it f of x. And I don't even care if it's not appropriate. Now I know that, this is the function, and the function is the output. And I've always just, I think for me this month, it just seemed like a function was something that it wasn't. You know what I mean? It wasn't ingrained into me that this function, if we put in values for independent variable, and we have one right here, this is just a function of a single changing variable, we're going to get a single number. That's it. One number. Hell yeah. And so if we chose this input of x, we're going to get that output, call it y of x, call it f of x. But that's our output. That's the number we're going to get. So sometimes I just like to be like, hey, that's a number. That's a number right there. Hey, this x, that's a number right there. And so, and check this out. This change in x, hey, great, that's also another number. And then so when I try to set up equations, I'm just like, well, what do I want to know about this? Well, maybe I do want to know its area. And so its area is its height times its base. And so that's this number multiplied by this number. Hell yeah. And I think even there, that's a less brain-melting way to start, to be like, oh, that number times this number. Okay, what is that number? Well, it's 1, so I could do that. It's 1. What's this number? I don't know. You know what I mean? This, we're changing it up visually. What is it? It looks like 1/10. Cool, 0.1. You know what I mean? And that's where you're not going to get confused, where, if this was a change in x of 1, it would be like, it would be all the way out here maybe. And then that would, make the problem a little bit difficult to actually visualize. We're going to make it that slice. Cool. And it looks like it's 0.1. Hell yeah, moving on. What's the area of this? Well, that's just going to be 0.1. And let's put in our variables now. So what is this number? It's y, so we could say that's y. And what is this number? This is change in x. And even right here, maybe I couldn't tell if I put this value of x or this value of change in x. Both are numbers. I just didn't know which one to use. I'm obviously trying to find the area of this little slice, so it's this one. But it wasn't obvious because I almost made the mistake and I almost put x right here. Okay, hell yeah. So then I can also say this is y of x times delta x. I can also say this is f of x times delta x. And cool. And what is this? Doesn't this look familiar? F of x times delta x. And when we do a derivative, you have f of x dx. Hell yeah. And then the crazy thing is that you'll have integrals where you'll have y dx, and maybe you're not understanding why this is y. You're just like, wouldn't it make sense to have x dx, because like these two things should maybe look the same, or why don't they look the same? And maybe that's a question you have in your head. I think that question can get answered if you say this y, what is it? It's the output, you know what I mean? A function's got an input and the output. And you can reverse a function. Maybe you know the outputs and you want to know what the input would have been. Cool. A function can go two different ways. But if it is the definition of a function is that if we have some sort of incremental number system for our independent variables, we're going to generate an output. And those outputs can be the same number. See how we have an output? Our input was 1, our output was 1. Input is 0, output is 1. So this one can't be reversed. If you did reverse this one, what would you say? So even just this is good for me. Okay, let's start with an output of 1. What's the input? I don't know. It could be 0. It could be 1. You know what I mean? Let's start with, and for this one, this output is the only output that we know. You know what I mean? Because all of our inputs generate an output of 1. Okay, hell yeah. And now I just try to dive into taking a very simple thing and let's explore it from because just no one uses all of those but anyway, I think we need to carry on. And let's see if I can even, I don't do this a lot, and I don't think I've done it formally of actually just setting up the integral. But if we do this once, if I take this value of x, which is a number, and put it into the function, which gives me another number, and then say I'm going to change x by a little bit, and which is this change in x, and then and I'm just going to say that change in x is real small, and I don't even care what y of if y of x gives me that value, I don't care what y of x plus change in x. And this is also a good way to write it. This is also the function evaluated x plus change in x, which is that point right there. So even though we said this was x and this is the value of 1, if I do change this by a change in x just by a little bit, now I have from this origin, I have x plus change in x. And if I plug that in to my function, that's my independent variable, x plus change in x, I'm going to get another number, a singular number because it's a function. But I just don't care what that is, because I'm just saying if I change this, it's probably close enough to what that last value was. And I'm always just going to try to say, hey, this is just a rectangle. For even if the problem goes up like that, and this is my value of x, and this is my value of change in x, even though it hits a new value, I don't care. I'm just going to pretend it's that rectangle. I'm going to have some error in that case. This is the only case where you're not going to have any error. And so, but hell yeah. Cool. And sometimes going from the simplest case is a little bit easier. Okay. Where do we want to go from here? Oh yeah, so just now we have the area of this slice. I don't even know what you call it. But we have, and sometimes you would call it dA. And this is a really good place. This is actually the most fundamental place where people kind of lose it. And I lose it all. I wasn't taught properly. I just figured, hey, we have an area, you know what I mean, which is going to be units of, let's say, meters squared. And if I took the derivative of this with respect to meters, you know what I mean? Look at this. I'm basically I'm lopping off a meter, So the derivative would be meters. And that's what, let's say that's what this, this represents. So let's say this is just the height. This line represents the height of this square. So if I plug in a value of 1, the height is 1. Plug in a value of 0, the height is 1 still. And so this function, my y of x, is units. I'll just do units. Units of meters. Okay. And then what is going to be the units of the integral? You know what I mean? Which we haven't done the integral yet. And the other thing from a fundamental perspective, the word integral comes from the word sum. And it's just because I've watched YouTube videos. And I was taught just from not this. I was taught never, you know, I'm sure the fundamentals were never taught or loosely taught or just, you know, everything in calculus is like, hey, we got a lot to cover. Let's just see how the math works. You know what I mean? And whether you get the proofs along the way and you can keep up with those, awesome, congratulations. But so that's where we're. All right, hell yeah. So new battery, and let's see if I can mess this up, because this is literally the crossroads. Like, I think everyone, you know, this is kind of a fundamental of finding the value, you know, changing it by a little bit, seeing that this is an area, seeing that we could calculate the area of this slice, and then, you know, kind of doing this on repeat. And there is no air here, you know what I mean? So we could just take the whole slice of this, which would be the function at x is equal to 0, which is the height, and then a change of x, and where the change in x is equal to 1, and then we would have the function evaluated x equals 0 is 1 times 1, and we would just have the area of it. So there's that aspect. I'm going to... The weird thing is that we call this area a change in area, you know, which is synonymous with dA. If I do have a dx here, this is infinitesimally small, where we have a small strip of area. It's so small, but it's but at least we, you know, and that's where it's like you wanna. Well, my brother says it's like I think that melts your mind. You know, just say it's really small. Like what's a small number? Like if I'm trying to drop a ball off of a cliff, like and time is equal to 0, time is equal to 1. What's a small number? I think a small number is 1,000th of a second. I don't even think I could stop and start a stopwatch, you know what I mean, in 1,000th of a second. So that's a very small number to me, and so I'm going to say that's going to be my change in time. And if I'm going to drop this for, you know, only like 4 seconds, maybe if it's a small something, like 20, you know, if it's 20 meters, it's like 2 seconds. And so I'm only going to have 2,000 increments. And that's a lot less than an infinite amount of increments, or a number that's infinitely small. And so there you go, that's small enough. Cool. And then so for our thing, cool, I can see that this is an area. I said the change in x was 0.1, and so there we have it. I gotta be thinking now. Alright, let's not, you know, I don't know how to solve it from a fundamental perspective, but maybe you have done an integral. So let's say we have done an integral where we're going to, you know, you've seen this, we're going to integrate this function maybe, and so that's going to be our function. So we have f of x, and then we're going to, and then maybe you've seen this, integration of our function is equal to f of x dx. Maybe you've seen it like this, integration of y dx, and maybe you've seen it where we have limits on our integration. We're going to go from 0 to 1. But let's do it from a fundamental perspective. We're going to go from x to x plus change in x. So we're going to go from x x plus change in x. And again, these are just numbers. Our input is just a number. That is just a number plus a number. And I think that's useful to know that there's not like, I don't know. I think that's useful for me to know that there's not like two things going on there. In one place where there's two things going on is the square root plus or minus the square root of x. Y is equal to plus or minus the square root. This is two functions. This is two separate functions. This is a function that says y is equal to the square root of x and y is equal to the negative square root of x. Now these are functions. Would be considered two functions. Two separate functions. And that's because this is a sideways parabola. And we can't have an overlap. This fails the vertical line test. Same thing if I have like an input of 2. I'm going to have negative 4 and 4. So an input of 2 gives me two values for my output. That fails the definition of a function just returning one output. You know, if my input is a number, my output's only going to be one value. The reciprocal is not true, you know what I mean? Because if I have y squared, and I have an input of 2 and an input of negative 2, my output for both of those is going to be 4. And so I have two different inputs that yield me the same output. So if I reverse this and I said, well, if I know I'm getting an output of 4, what input is it? You know what I mean? I don't know. Hell yeah. Alright, and let's use common tactics on this to figure it out. So we're going to have x to x plus change in x, and our function is just going to be 1. And so we just have d of x, and that's going to integrate to x. And so we're going to have x evaluated at x, and then x plus change in x. And to evaluate this, we're going to have the second minus the first. So we're going to have x plus... Alright, hell yeah. So we're going to have x plus delta x, and then minus the first, which is x. And then so the x and the x minus x goes away. And so change in x is our answer to this. Our units on this was meters, and our units on this was meters. And so the units on this is meters squared, because we have a 1 here, you know what I mean? This 1 dx was our meters times meters. And so if I'm yielding this term, which is just x, this is going to be in units of meters squared. That's difficult to see, but that's true. Just think of this as a 1 times x, anyway, hell yeah. Where this is my height. Yeah, that's totally graphical. This is my height. And then the x is just my width. If I say x is equal to 1, I've made a block that's a 1 by 1. If I say x is equal to 2, I have a height of 1 still, and then a block where this x value is 2. And then so that's going to be there. So that's where even a basic equation, I don't even keep up with the units. And so, hell yeah. Cool. And then the other thing is that, well, and we'll try to get to that in a sec. I think it's hard. I think putting limits of integration on this is useful. And I even skipped the step that when we did the integration, I just said this was 1. It should be 1 plus a constant. Because anytime you integrate, you get a family of equations. And I think that's... for what I'm doing here, like I don't even, it's really difficult to explain. Just because you have to look at this from the integral of this equation is another equation where if you took the derivative of it, you would get back this equation. And so that's all, but yeah. And I think that's where, and we'll try to get into that in this video. But right now we have this solution where this is units of meters squared, which is area, and our area is equal to 1 times change in x. And that's what we have here. We have a height of 1, and we have a width of change in x. And so by summing, and so this integral sign is a summation sign. And I wanted to do this one because this is where you're just summing once. And I think that's cool because I think that's an intermediate step to be like, well, now I want to sum 2 of them. Now I want to sum 3 of them, 4 of them. I want to sum this direction too. I want to start here and make these equal with change in x. I could have, if my change in x is 0.1, I can have 10 of them. And so to get the area of this, I'm going to do 10 of those widths, and then I'm going to add them together. But what we did is we just summed 1 of them. And so we did the summation of I is equal to 1, you know, and then you would just say to 1 up here. But I was telling my brother, it was just like, I like to say, you know, if it's summation of I is equal to 1 to infinity, I like to write the summation sign as I is equal to 1 to I is equal to infinity. I think this extra step above the summation sign, and this could be k, it could be the summation of n is equal to 1 to n is equal to infinity, the summation of k is equal to 1, k is equal to infinity, or I is equal to 1, you know, I to infinity. It could be j is equal to 1 to j is equal to 1 to j is equal to 10. Doesn't have to be infinity. You know what I mean? So, but I think that's useful. So what we're doing is we are yeah, and this is also, yeah, summing one thing is a fundamental that I should be able to do. And so what are we actually, I don't want to grab another card. But, yeah, we will. We'll just do another sheet of paper. So, hell yeah. So, we have y. We have x. You could call this f of x. Our function, you could call this 0x plus 1. That's another way to write it. And, hell yeah, you just call it y is equal to 1. Well, no. That's this function. This is just the output. So if this is our input, this is our output. All right, so let's find a value, and we're just going to say that's 1 and a height of 1. We're going to come out here to a value of x. So this is our value of x, and then this point right here is xy. And that point is x, and we know its height is 1. And we're going to do a change in x, you know, of 0.1. Cool. And that's the visual slice that we get. And where were we going with this? Oh yeah, and I want to sum these up, because maybe I had a second one, you know what I mean? But I don't want to add that one yet. I just want to add that slice. And so how would I do that? I would say, well, what's the area of this slice? And I'm going to say this is a change in area. Like, I don't even know, like that fundamental I haven't gone over yet. I don't even know why you would call this a change in area. I kind of forget why. But yeah, change in area is evaluating the function at x, and then multiplying by change in x. So that's our, you know what I mean? Hell yeah. And yeah, what does the integral look like? The integral looks like f of x dx, where you would sum. And this is for summing all of them from negative infinity to infinity. We did the example where we're going to sum from x to x plus change in x of f of x dx. And I was just going to show that this is just equal to summing once. So I'm going to have f of xi, where I is equal to 1, and this is integers. When you're summing, I think this has to be integers. Series has to be integers, but this is just I is equal to 1 to I is equal to 1. So you're just doing it for one iteration. If this was 2, you would have I is equal to 1, and then you would have that output, and then you would have I is equal to 2, you would have that output, and then you would add them. And I think that also gets confusing because we still have a function here. A function can only kick out one number. Cool. But then we're going to add it to another number. And I think that actually is a head trip because we, from the fundamentals of a function, and maybe that's hard to see. Because you have summation signs and functions, maybe you think a function can be a bunch of numbers, because of this. But no, this can only be one number. But this says, how many times we're going to add it to another number. And in our case, we're only going to do that once. So hell yeah. And then we have change. So we're going to take that value once, and then we're going to do this change in x. Now, does this get an I? Well, I don't know. Let's see what we would do to the second one. If we actually added this second one, we're at a new x. That second one is actually now at x plus change in x. Cool. And and this width is still change in x. So that would be the second one. And maybe I even have this, totally, I don't know, maybe I'm just actually not even writing the summation correctly, because x of 1, how do we know what x of 1 and x of 2 is? I think we actually have to write an equation for what x of 1 is. X of 1 was just going to be x. X of 2 was going to be x plus change in x. And then x of 3 was going to be x plus change in x plus change in x, which is x plus 2 change in x. And so even here, we could write this as a series. I'm going to pause the camera. All right. Hell yeah, I love pausing the camera for a couple seconds, because what I did is I'm going to change this value to what I'm used to. Series, I like to use the, they're going to say a series is like an, where you have n. You know what I mean? And you would write this as an is not the summation. No. I guess that's different. If this is a series, this is just, where n always starts at 1. And I don't know if that's across the board. If there's two schools of thought where sometimes n starts at 0, 1. I don't think so. I think from the two books that I've looked at, maybe just one, maybe just James Stewart, in that section on the multivariable calculus, because they go back to series, and they say that n starts at 1. If you're doing a series of numbers, and so that's this, so we're going to have a series of 1, 2, 3. Now this an just indicates a series. S of n is the summation of that series. It's the summation of an when n equals 1 to infinity, which I would write the summation of n is equal to 1 to n is equal to infinity, because then it shows that starting point, that finishing point, and then of that of these individual values. And so this value right here is a1. This value right here is a2. And so if we said the summation of and that's an. If we chose I, you know what I mean? If we chose I is equal to 1 to I is equal to 10 of Si, then we would have where SI is, I'm sorry, of AI, because this would be the sequence of numbers. Whether you're talking about AN, I mean, you could have AI, you could have AK. This letter is arbitrary. So is A. You know what I mean? But typically, when it one of the books, it showed a series using the letter A, and then the letter N. But I think it gets confusing when summations might choose the letter I. You know, or summations, because if you have to do multiple summations that are different, then you're going to choose like J. Then you're going to choose K. K1 to whatever number. Could be infinity, it could be 5. To 2 or infinity. And this is also J equals. This could be K equals. Alright, hell yeah. So for this first value, I don't have a change in x, but for the second one I do. I have one of them. Here I have two of them. So I start with 0 of these, and then, but you know what I mean, my series don't start with 0. They start with 1. And so the easiest way to do that is I'm going to say this x1 value is x, check, and then n minus 1. And this is where I switch to the n's. Because if this is going to be n is equal to 1 to n is equal to 1 of f of x of n delta x, x1, you know what I mean, is xn when n is equal to 1. That's x1. I know that's going to be this value of x. Cool. And I know I'm going to multiply by change in x. I'm always going to be multiply change in x, so I'm not going to have an n here of, or you know, like your, and I'm going to go reference back to here. I'm just going to switch back and forth between, like I said, it doesn't matter if this is an n or an I. They're just letters. Cool, but x1 is going to be this x. I'm going to have that n is equal to 1 somewhere, and so I'm going to have n minus 1. That's going to be 1 minus 1 is 0. 0 change in x. And then for the next one, x2 is going to be x plus n minus 1 change in x. N is now 2. And so we have x plus 2 minus 1 change in x. 2 minus 1 is 1, and now I do have that change in x. When n is equal to 3, we're going to have x plus 3 minus 1, which is 2, plus 2 change in x. And so hell yeah. So now we have our what our x values is. So we can do this summation of n is equal to 1 to n is equal to 1 of f of, and maybe, you know, for visual, let's do it 3 up here, and then we'll change it back to 1. But just because we did it 3 times here. And then these values are going to be, for our x right here, for our xn, xn is going to be, so yeah, our equation for xn, just like we would have an equation for an, and we haven't summed anything. That's the crazy thing. I just want to change my independent variable and get a new output. Change it to this value, get that new output. Change it to this value, get that new output. Guess what? There's not even a correlation. When I choose this as my input and get that as my output, those two are linked together, but are completely separated from there. They're related by an equation, but they're completely separate. And I think that's useful for me to see. Cool. And how do I write? So that's where this is a series, and now I can see that. I can see that this is equivalent to that an, and I think it's just bizarre to have a series where a series of 1, 2, 3, and this is the simplest series. So if we're starting with the simplest cube, what's the simplest series? 1, 2, 3, 4, etc. And this is how you would write it. This is also a series xn, 1, 2, 3, 4. This is x of 1. This is x of 2. This is x of 3. Just like this is a of 1, a2, a3. And then so somewhere down here we would have ... a of n. Now n could be infinity. You could have a infinity be the number infinity. But if you're just choosing any one of these at a midpoint, you're just going to say, hey, that's x of n. And so even though you would have x of n be your last one, but it doesn't have to, it can still be a midpoint, because what if you had x of n plus 1? There's no cap on this. You can have x of n plus 1. Hell yeah. And then still have plus ... plus a infinity. Nah, because then you could have a infinity plus 1. But I think I'll have to look that up. Because if you have, like, hey, this ai term, or xi, which is just one of them, and it could be any of them. That's why we're summing from, I is equal to 1 to I is equal to some sort of number. It could be infinity. And that's kind of fascinating. That's where the integration, all this sign is the summation of I is equal to 1 to I is equal to infinity. And I've seen that in a YouTube video. It doesn't really hit my brain until I actually go through this verbiage and be like, oh, no, duh, I see that. I see that this is a special case where you've made so many little slices in here because you've made them dx width, which is infinitesimally small, and then we're going to sum them all. And this has a special term. It's an integral sign. Alright, hell yeah. But if this is an integral sign, you know what I mean, and it's related to a summation, I just want to sum one of these things, because that's the simplest, I can't sum 0 of them, you know what I mean. I have to sum at least one of them to get that one value, which is just the area of one of those. And so, hell yeah, we're almost there. And so we're going to do the summation of n is equal to 1, and I'm just going to put a 1 up there, knowing that you can also, it's n is equal to 1 to 1. And then we'll do it with i's as well. The function where x of n is this series, and the series is this. This is x. Well, no, x1 is where n is equal to 1, but this is xn for all of them. This is the same for n is equal to 2, same as n is equal to 3. So my function right here is x plus n minus 1, change in x. And I would like, my brother does, like stuff like this. My brother, 7th grade math teacher, I was just like, oh, you do summations in your class. And he was like, I don't know what you're talking about. I was just like, but you do, because he always gives like challenging problems right at the beginning that are real world, that require you to not just do one input. Like a 2 plus 2 is 4. It's a combination of inputs. Maybe it's going to be 2 plus 2 plus 3 plus 3 plus 4 plus 4. Something like that. A real world problem where, you have to do this, and then you have to do it 50 times. And then you have to be like, cool, you have about 10 minutes, do your best, try to do whatever you want to do. And then all the students go different routes, and it's really fascinating. But that's like I don't see these very easily at all. So it's just these are, and no one wants to go back and figure out how to put an equation on a series because it's a friggin' puzzle. You know what I mean? But hell yeah, I do like this because it is a puzzle, and from just kind of like doing stuff like that, well, writing it all out, and then seeing if I see a pattern. And even if I miss the pattern, like this n minus 1, you're like, oh, like the second you actually ingrain that in, then you're like, okay, now I know that like that was the trick. And then you don't have to like relearn the trick every time. All right, hell yeah. But this is x of n. Hell yeah. And then we have delta x. So there you go. And if we did it with i's, we would have the summation of I is equal to 1 to 1, f of x of I, change in x. So you would have it like that, or you would have the summation of I is equal to 1 of f of x my bad. This would still be xi. Nope. My bad. This, if I wrote it like this x, how do I write this? If this was x, my bad. This is xi, where I is equal to 1. This is xi, where I is equal to 2. This is xi, where I is equal to 3. And the general equation is xi. So this right here is xi, where this first value is a constant. This is a chosen constant. This is a chosen constant. The only thing that's changing in this series is this value of n. So in a series where you have a of n, everything else is constant except the n is changing. So if I have a of n is equal to n, where n can be 1, 2, 3, etc., then that's the only thing that's changing. If I have a of n is equal to 2n, where n is equal to 1, 2, 3, the 2 does not change. If I have a of n is equal to xn, where n is 1, 2, 3, 4, this x is considered non-changing, constant. This isn't, even though that's like, this would just be an input. Sometimes if you have that, that's where we use k, because k is usually a letter for a constant that's non-changing. So if I have an is equal to kn, then I have n is equal to 1, 2, 3, etc., where k is constant. And so I think that's where I could even write it like that. I could write the summation of n is equal to 1 to 1, f of k plus n minus 1 change in x. And so that's what we'd have there. And this whole thing would still just be x of n. Cool. This chosen value of x is just my initial value of x. Oh, and you can represent that as x naught. So there you go. So that's another term. If x naught means that's unchanging. But this x isn't even x naught. It is x1. So that's fine. I could, yeah. So let's. I want to keep plugging. All right, hell yeah. So this is my value of x. Here's my strip. It's about 1/10, 0.1. This is my, so at x, this is my value, and it's 1. And if I did have 2, you know what I mean? But there you go. But one of them is taking that value, and this is, I'm going to write f of x. I think this is, for calculus, you could call it y, but I think it is good because you have this independent variable. And all a function is putting it into a function where, you know what I mean, you actually have something x. So this is how I write a function. I think if you say y is equal to something x, that's a little bit helpful. But I think it's crazy when you have y is equal to 1. Because you're just like, where do I input the x? Because I could have x is equal to 0, 1, -1, negative infinity, positive infinity, infinity minus 1. You know, the whole range, all real numbers. But for our case, I could have x as anything between 0 to 1. And I would represent that as x. I would do this, which is also good. X is established between 0, 1, where x is in between. It's going to be less than or equal to 0 and 1. So this is a function. So f of x for all values of x between 0 and 1, and can be equal to 0 and 1. Hell yep. But yeah, so if f of x is equal to 1, where do I input the x? And that's where we see this is a horizontal line, slope of 0, and that's where I think it's very useful to use y is equal to mx plus b and just see that the slope is 0, and there's the x. The y-intercept is 1. And so we have slope of 0x plus 1 for our equation, and now we can input a value of x. When we input a value of x is equal to x, and we can consider this x to be our x1 or x0, but we're going to consider it to be our first value of x, where this is our second value of x. So this is going to be x1, this would be x2, and we're going to take this value at x1 and then just whatever this value, we're just going to assume it's the same at x, at the change in x. And then we're going to say that second, for this area, we're going to use that value, which is x plus change in x. And we're going to call that x2. So x1 is just x plus 0 change in x. This is x plus that, and that's where we got that series, x plus 2 change in x. And so, yeah. But I could say, because, you know what I mean? I could say this is still x0, because there is a difference. Just because we took x0, added it to 0, delta x. Just because this was 0, we didn't know it was going to be 0. And so, hell yeah. So I'm going to call this initial x x0. And I think this is useful, because now it's our first established point. Now we just lock this in. This is no longer a changing variable. This is just a number. And I think that's useful. Where we just had an arbitrary x, I think that is typically of like, hey, that variable can change, on a scale that makes sense. For our problem, it would make sense if it was 0 to 1. Like that would be our value for x. And I think that's also, if we're starting, if this is the formal way to write it, hey, maybe this is 0 to 1. Maybe that's something that you could adopt, just so we're like, hey, x is 0 to 1. Write this in a bunch of different ways, and then, hone in on maybe what's formal. But sometimes I don't like what's formal, just because it's like one more thing that's taking up your brain, and if you have to jump through all the hoops just to tackle something, I don't like that aspect. Alright, so hell yeah. So we've established now that this can be x0, and I do like that. And now we're going to start adding one of them. We said that, well, what about xi? Oh, there you go. So here we go. We have x1, x2, x3. Maybe I want to know is 100, but I want to know an equation for that. And so I'm just going to call it xi. We can also call this xn, where n is equal to 100. Two different ways. I'm going to be honest. Sometimes I like to see this I, especially with summations. I is equal to 1 to whatever. But then with series, I've been learning series where I want to see that n. So whatever you want. Like I think this, if this is my series n, where I know n is 1, 2, 3, I think it would look weird to me if I saw ai is equal to I, where I is equal to 1, 2, 3, 4. It's just a letter, but this is messing with my mind, and this seems like, oh, that seems to be some sort of standard that they chose, but this literally is just a letter. Alright, hell yeah. And this is very synonymous with like the 6-hour videos of like that one that went viral on the problem, because like, hey, all I'm trying to do is get up to the point where I don't know what I don't know. You know what I mean? And that is where we're trying to do the integral once. And then once we do it once, we can do it 10 times, We can sum 10 things. Alright, hell yeah. We got a new battery in, and we're almost there. The area of this, we're going to go to this x0. Let's just say what we're going to do. We're going to go to that x0. and we're going to put it into a function. And that's going to yield us a value of 1. We're going to multiply that value by changing x, which we know is already 0.1. I think that's very useful to already have established numbers so you kind of know where those numbers are. Once you know what the numbers were from an intuitive perspective, now that we have 0.1 with units of meters squared, meters squared, then we can go back and put the symbols into them. And so how did we get this singular value? Well, we put in a singular value of x. This, we're not just saying f of general x, but we could say this was f of x. And we put in this value even though we just needed to put in that x naught. And so let's call this xi, or we could call it f of x1. That's actually what we put in. Just because for the second value, if I'm going to try to get the area of that one, what's my value that I'm going to put in there? Well, I'm going to put in f x naught plus change in x. And then the next value, I'm going to put in f, if I'm going to try to get a third area, I'm going to do f naught plus 2 change in x. And then so what about an ith? The ith, value. Well, it would be f of x naught plus, this was the second one, because we had, this was the first one, first, second, third, ith. What would that be? You know what I mean? I have one of those, I have two of those, I have two of these when this says 3. Okay, so let's just say, and this, I can use this value, I can use this number, because that's what we do in series. We say, hey, we're going to start with an n is equal to 1, and then n is equal to 2, n is equal to 3, and n is equal to I. And maybe that's a good crossover. I just use n is equal to I, I think that's a good, even though I'm saying the same thing. I think this would be more sensical if you said I is equal to 1, I is equal to 2, I is equal to 3, I is equal to I. So let's write that. I is equal to 1, I is equal to 2, 3, I is equal to I. Because, hey, this is f of x I. That's what all of these are. This is where I is equal to 1, I is equal to 2, I is equal to 3. This value is only 1. So when I is equal to 2, delta x, there's only one of those. When I is equal to 3, delta x, there's 2 of them. So this is the pattern recognition. At I is equal to 1, delta x, there is 0 of them. So then we would say, well, if my I term is 1, I'm going to go 1, I'm going to take that I term, which I know is 1, and subtract 1 to get 0. So that's what I did. 1 minus 1 is 0. This is going to be the I term minus 1. And then that's it. That's the component of that. And so now, for x of I is going to be I naught plus I minus 1 delta x. And so if this was the 100th term, I would have 99 delta x plus x naught. And so so that checks out. You know what I mean? If I is the second term, 2 minus 1 is 1. And then we see right here, this is the second term, that's what we get. So here is our general equation. And that's where seeing this I doesn't, I don't know, I'd rather see an N there. Just because the letter I is really skinny, and that bothers me. You know what I mean? Where N looks like it actually fills up a number. Yeah, I mean, isn't that weird how you see an I and you're just like, it's too skinny to be a number. You know what I mean? Yeah, I don't know. That's where we kind of crossed over. I said n was equal to I. And then so maybe I want to do this f of x of n. See how these are just, it doesn't matter what letter you put there. Maybe it does, but I don't care. All right, hell yeah. And then this is where I like to be like juggling. You know what I mean? I could probably do this, and after I do this video, I could probably do this in 2 seconds. I'm just going to put in a generic x there, generic change in x. But I kind of know that that's going to be x1, and I kind of know that's going to be x2, that's going to be x3. I just want one of them. And so I'm going to, you know, get this value, which is f when I put in x1. It's going to be 1. That's the height of this, and this is 1. Cool. And so the area of it, and I could just call it an area, or I could call it a change in area. I don't even want to do that. I just want to, you know, make it look like f of x1 times change in x, which seems very similar to this integral of f of x dx. And I want to know why that's the case. And this is, we're just going to sum one of them. So that's what I'm going to do. That's why I'm going to have the summation of, and that's where I'm going to put an I here, of I is equal to 1 to 1. And now these are starting to look similar. We got our equation for xi, you know what I mean? It was some, it was, xi was some initial value of x, which I mean, should I call, I can't use it xi, that would get confusing. I could call it x naught. That seems cool to me. I could call it, yeah, x1. Could I just call it x1? Could I have where xi is x1 plus I minus 1 delta x. I think I could do that. I don't see why I couldn't. Let's just do what x1 is. x1 is x1 plus I minus 1 change in, oh sorry, well the I is 1, which is x1 plus 0 change in x. x1 is equal to x1. I mean, it looks legit. You have an equation equal to an equation. And so, hell yeah. So this is going to be, and this is a series. Because I know that I'm taking I can be 1, 2, 3, 4. And maybe I just haven't worked series enough to just kind of know that this is so fundamental to a series that series never start at 0. Maybe they do. Maybe there's a way to, I mean, that's why we shift them. I don't know, I'll have to Google that. It's a real quick Google, just to be like, hey, any math books, is there any series that really like to start 0, 1, 2, 3? Or do they all start with integer values of 1, you know, starting with 1? Because 0 is not an integer, I guess. Is it? Don't know. Alright, hell yeah. So now we have that equation. And that equation can go right in there. So we have the summation of I is equal to 1 to 1 of f of x1 plus I minus 1 delta x. Delta x. Hell yeah. Alright, sweet. And we know what delta x is just an input number of 0.1. We know that. And we know that we're going to, x of 1, let's just choose it now. You know what I mean? Let's just choose it's 0.5 right in the middle, 0.5. Cool, so x of 1 is 0.5. Hell yeah. And so x of 1 is 0.5. Anything else? I is just going to be 1, because we only have one of them. We're only going to sum one of the terms. And that's everything. There's that, and that. Okay, so let's write it again. So we have the summation of I is equal to 1 to 1. And that's why I'm doing this. I swear, summing one term is mind-melting. And so, cool. So we have f of 0.5 plus 1 minus 1 times 0.1 times 0.1. And then so this is the summation of I is equal to 1 to 1 of f of, this is 0 times 0.1, this is 0. And so we have f of 0.5 times 0.1. We have our function. Now we can, we should have wrote our function. A function of x is going to be 0x plus 1. We wrote it like a line. And now we're going to input 0.5 in there. Like obviously 0.5 is going to be 0 times 0.5 plus 1. Obviously it's going to be 1. I mean, that's obvious. But that's why we're doing this, because it's not obvious to use this as your equation, a linear equation where your slope is 0. Hell yeah. And so this value is 1, and this value is 0.1. So now we have the summation of I is equal to 1 to 1 of 1 times 0.1. And now we're just going to sum, we're just going to have that one value, because we only did one iteration. We did our iteration, and it was that. And I think you can get rid of the summation. I think once you actually right here, you get rid of the summation sign. Because, I mean, if I had I is equal to 1 to 2, I would get rid of the summation sign and then do f of the next one, which would be 0.5 plus 2 minus 1 times 0.1. You know what I mean? And, hell yeah. But I don't have, so that's where you would get rid of the summation sign, because you're already summing. I'm not summing them all up and then just putting a summation sign just for fun. Like if I'm writing out the summation sign is redundant. Yeah, I'll have to ask, like, is there any application where you would still include the summation sign after inputting the value, for the summation? So if it's I is equal to 1 to 3, if I wrote out all three sums, this should go away. I mean, that's just the sensical thing. But that's where I didn't. It wasn't obvious just to get rid of it. It felt like I had to carry it all the way through. But nope. So we get rid of it from this step to this step, because we just summed it. We summed one term. And even though we still have to put in this, it's a function, it doesn't look like a number yet. Well, a function of a value is a number. And this is already a number, we see that. But that's where, again, seeing the function, it's very difficult to be like, oh, this is a singular value. If we're inputting, if we're setting up, if we inputted the numbers for the independent variable or variables, this is just a function has to output a single number. Cool. And that single number for this is just 0.1, and we're done. So hell yeah. So that's the equivalent of integrating from x to x plus change in x of our function 0x plus 1 dx. That's the same thing we just did. Sorry, not dx, but change. Well, no, dx. This would be a dx, and then this would be a change in x. This change in x is 0.1. This dx can be 1,000th, and then we'll have 100 of them, 100 slices. This could be 10,000ths, and between whatever value of x we choose, 0.5 and 0.5 to 0.6, we have a difference of 0.1, and if we do slices of 10,000 slices, we'll have, or if this is our change in x, we're going to have 1,000 slices. dx says, hey, you're going to have more than 1,000 slices. You're going to have 10 to the 10 slices. You're going to have 10 to the 10 to the 10 to the 10 slices. And then it's just, ridiculous. But hell yeah, infinitesimally small. Okay, so hell yeah. And so we just showed how we, and yeah, so we didn't, you don't use the integral sign unless that change in x gets really small. And this change in x gets really small if, how how does this change in x get really small? If you have a lot of them. If you make this change in x real small. Yes, you could either, if you make this change in x real small. Yeah, and I don't even know how to write that. You know what I mean? Because if you wanted to, if you started at here, and you know x naught is equal to 0, and you wanted to get all the way to 1, if you chose a change in x of 0.1, you'd have 10 slices. If you chose a change in x of 100th, you'd have 100 slices. If you chose a change in x of 10 to the negative 10, you're going to have 10 to the 10 slices, because here you have 10 to the negative 1, 10 to the negative 2, and you're going to have 10 to the 2 slices, 10 to the 1 slices, 10 slices, 100 slices, 10 to the 10 slices. If you have change in x is dx, is, you know, that's 10 to the negative infinity. And then you're going to have 10 to the infinity. I mean, you're going to, yeah, you're so infinitesimally small, and so that's kind of, I forget how they actually do it. But yeah, you make change in x real small, and then you have to take your I is equal to 1 to infinity. The only way I can be infinity, oh, and that's the reverse way of saying that. If I'm going to start with this square, and then I'm going to make a slice that's this width, or it doesn't even matter. Forget what the width label is. Change in x, you know what I mean? But I'm going to have an infinite number of them. Infinity fit between 0 and 1. If I did have an infinity of them, of these little slices I have found area of, what would their width be? They would still have to have some width, because they can't not have no width, you know, because of this relationship. See, that's, I don't, like, I'm a literalist, where that literally melts my mind. But yes, if I had infinity of them, well, let's say I had one slice. One slice, the width of that slice is 1. So if I had one slice, the width is 1. If I had 10 slices, the width is 1/10. Cool. So there you go. So 1 is to 1. If I had 10 slices, is to 1/10. If I had an infinite amount of slices, the width would be 1 divided by infinity, which is approaching 0. So there you go. I think that I see. Infinite slices, the width of each slice has to be 1 divided by infinity. And that's what we're calling dx. 1 divided by infinity is dx. Infinite number of slices is just infinite number of slices, which is summing this sign. Summing an infinite number of slices. Even if you sum an infinite number of slices between 0 and 1, there's still an infinite number of slices there. If you're doing the indefinite integral between negative infinity to infinity, still an infinite number. You're starting at negative infinity to positive infinity, and then you're doing an infinite number of slices. I think that's a weird thing to think about, but each of those slices will be 1 divided by infinity. Don't quote me on that, but that just seems like I'm just trying to have more mental ways so I don't just bleed my brain when I see this dx. I think it's you can have a better understanding by always saying change in x, and just know that your change in x has to be really small, and if it's not so small it's approaching 0, you're going to have error, but you're going to approach the right answer. But that's all limits are. They're approaching something anyway. Alright, so I think I summed one slice, and I think we compared it to an an integral sign, where we put limits between x plus x. I guess the only thing we didn't do was, like, do the integral of x to x plus dx. If I see this dx, though, now I have a visual. So 0x plus 1 dx of this. And then, rules of integration. Well, this is just x plus dx of 0x plus the same integral x plus dx of 1 dx. Sorry, there's a dx here. But this is always going to be 0. 0 actually goes out. My brother was showing me this. You should always use these things, just to, because especially when doing proofs, you'll have things that just lop off and simplify. Well, 0 outside, whatever I'm doing in here, is always going to be multiplied by 0. Because that's what this is. This is x dx. You know what I mean? I'm going to integrate that. Integration goes to x squared, 1/2 x squared. But all of that is just still multiplied by 0. Plus a constant. But all right. And then so that boils down to this. And this says, cool, this is our 0 to 1. We chose an x, and we chose a dx slice here. Our limit, and this is our value of x. This is our dx. And what this says is that, no, that doesn't say there's an infinite number of slices in between there. It says that there's, what the hell does that say? That's interesting. I guess infinity is a concept. You can't say infinity plus infinity is 2 infinity. Yeah, so that's another conundrum. I thought there was going to be an infinite number of slices between dx, but no, you've already infinitely sliced it. If you see a dx, you've infinitely sliced something, and this is just one slice of those infinite amount of slices. The weird thing is those infinite amount of slices could fit between negative infinity and infinity, or the same number of infinite slices could fit between 0 and 1. Does that make sense? I mean, mathematically, I think that has to make sense because infinity is just a concept. It's not real values. And so, but that also sucks. That seems mind-melting. Yep, because I was going to show how there was like an infinite number of slices between this dx, but that's not true. dx, by definition, means that you've taken an infinite amount of slices and you've taken the width of that one slice. So if you could take an infinite amount of slices and then have one slice, what would be the width of that? Well, I mean, it's 0. It's approaching 0. It's not 0. And that's where it's just like change in x is never 0. You know what I mean? Dx is never 0. It's approaching 0. And so, hell yeah. And like I said, I have to do these videos before I can actually ask, Google AI intelligent questions, or because AI is remarkable, because even in textbooks they're not going to cover bizarre stuff like this of just like trying to, hey, I just want to know the fundamentals. And maybe they do cover it. It's just, technical proofs are very difficult to chalk out the good stuff. All right, hell yeah. So that was it. That was crazy, but I think I did what I wanted to do. I'll have to figure out where this summation of something, change in x, like how do you do the limit? You know what I mean? Where in this does the change in x, how do you reduce that? I forget how to do that. Where do you get the integral where this becomes dx? Is it just the limit as change in x goes to 0? Is that all? You know what I mean? If you have the summation, I guess we got to do that. So let's try that and see if that actually... That's the other thing, is like if you recall something, and if I watched a video, I wouldn't come back to this. I just want to be done with this. So we're some value of x, a change in x. We're going to have a summation of x, I is equal to 1 to infinity. I think so. But that's for the whole area of this. That's if this was our equation, 0x plus 1. How much time do we have left? Hardly nothing. All right, we didn't lose anything, thank goodness. All right, first up, yes, this is an indefinite integral. And it goes from negative infinity to infinity. So yeah, and it represents this, I is equal to 1 to infinity. But still, if I have 0 to 1, I still use the same dx. 0x plus 1 is our equation, 0x plus 1 is our equation. I still use the same dx, and I think we covered that. Chopping 0 to 1 into an infinite number of slices is the same thing of having this function go from negative infinity to infinity and chopping this function into an infinite number of slices. There's an infinite number of slices between 0 and 1 as there is between negative infinity and infinity. Man, and I don't think that ever gets told. And I don't know if that's 100% accurate in saying that. But still, you have an indefinite integral, which they just show like that, which is also criminal because, like, I don't like shortcuts like that. Like, if this integral always means negative infinity to infinity, just a few times it's very helpful to be like, hey, the integral of 0x plus 1 dx is equal to the integral of negative infinity to infinity of this equation, and maybe this is not equal to the integral of 0 to infinity. Is there any way that that would be possible? That it wouldn't be equal to that? Dx? I mean, if you had an equation, just stop and then do that, but that would be discontinuous. I don't know. I guess, I don't know. But anyway. But at least that part. Okay, so what were we trying to do? Yeah, so I guess even though we have our box here, we're going to have this equation 0x plus 1. And if we're going to sum from I is equal to 1 to infinity, of some value of x, and then some slice dx. Knowing that we did divvy this up infinite amount of times between positive infinity is negative infinity, we have some sort of x. I think it's useful to be like, hey, this x could be over here, and then the change in x, and we'll just say a positive change in x. And, this is equivalent, and this could be x. This is just where x would be a negative value, but x can be all real numbers. And so, is that one way to say that? We did this. X can be negative infinity. It can't equal, so it's just got to be x is greater than negative infinity, less than, because infinity is not a number you can encapsulate, and that's how you would write it. Hell yeah, you'd also say, would you write it like this? I don't know. X is all real numbers between negative infinity, infinity. You can't do it this way because this is saying that these values are, you close it into that value, and that means that value counts, where it could be equal to that value, and that value would be nonsensical. So you write it like this. I just don't know if you say where you put this. When you write it like this, where do you put the x? Saying x is equal to values from negative infinity to infinity. Oh, we were really slow rolling this one. And it's just because I've never done it. I just want to be able to do it intuitively myself instead of just watch a video and then forget how to do it. I think that's the most important thing. And just see like where I muscle my way through. And we want the area of this slice. Essentially, and we're going to call it dA, where dA is going to be summing. Well, no, dA is just one of the slices. I want the, what do I want? I want the area of this whole thing. Oh, and that's trippy, because an indefinite integral, if you integrate 0 x plus 1, is basically integrating 1 dx, and you get x plus a constant. That's the equation you get. But if you integrate from negative infinity to infinity, you're going to have infinity plus a constant minus negative infinity plus a constant, and into x. And so, what are you going to get? And you're going to get 2 times infinity. And does that make sense? Because if you're starting at a 0 point, you're going to get infinite this way. You're going to get an infinite length this way times the height. And the height can be, 1. No. Yeah, the height is 1. So if we went infinite this way, I would have infinity times a height of 1. If I went infinite that way, I would still have infinity times. So I should get 2 times infinity. Oh, and this is where my brother didn't say anything about infinity. Yeah, I can use the number infinity. I can use number negative infinity. I just know it's the smallest number I've ever known. Or it could just be negative 0.001. Good enough, you know what I mean? And, but hell yeah. And so even if I did that, if, I'm sorry, not the smallest number. Negative infinity is the biggest negative number. Negative 0.001 is just approximately 0. Negative infinity is like negative 10 to the 10, 10 to the 10 to the 10, negative a big number, negative a million. You know what I mean? That's big enough. And for a big negative number. And so if I put in negative a million, and then a million, I got a million this way, negative a million this way, the area of this, and, you know what I mean, it's only going to be positive if this function is above the x-axis. Just because we took that independent variable here, we got this value, that value was 1, positive 1, and cool. But from negative a million to a million, our area would be 2 million. And so from negative infinity to infinity, if we are going to do this as a definite integral, negative infinity to infinity, which is, this is an indefinite integral, but if we treated it like a definite integral, yes, we would integrate this 1 dx becomes evaluated x plus constant from negative infinity to infinity. We would do infinity plus a constant minus negative infinity plus a constant. This is going to be infinity plus a constant plus infinity minus a constant. The constants cancel and we get 2 infinity. Hell yeah. Huh. Yeah, so that's cool. And back to the summation. In the summation of this, I just don't know how you're gonna, it seems like you have to start at negative infinity. And that's the part that's tripping me up. It seems that if I'm actually going to, you know, have a starting point between negative infinity and infinity, and then pick that starting point for my x1 value, and then add a change in x. So my x1 value has to be negative infinity. My change in x has to be a dx. And so I would have to already start at that negative, and that's probably what's tripping me up. And so, so to get the entire area from negative infinity to infinity, I got to sum I is equal to and maybe I'm tripping things up. Maybe they don't, maybe they only do half of it with this. That would make sense. If we start at 0, let's just do that. So let's say we know that we're going to start at 0 and go this way. And we're going to try to find the area under the curve. That's going to be the integral of 0 to infinity. And I don't know what you would call that integration. But that makes sense to me, f of x dx. And we're going to start at a value of x is equal to 0. But we still need this function, x of I. And then we're going to have change in x. And this change in x is going to be dx. It's going to be very, very small. And then we're going to have I is equal to 1 to infinity. And this is going to be where our change in x is going to be 1 divided by infinity. I think that's the relationship there. I forget how you even show that. I think they would just do like I is equal to 1 to, I don't know where you do what number that you put here, and then do the limit as change in x goes to 0. So I'll have to watch those videos. So I'm done with this. I mean, I got to the place where it makes sense to me. I kind of understand what we're doing. I'm ready to look at technically how they actually write it. But I think this was good, just exploring with, summation signs, seeing this function, knowing that this is just a singular value. If I see delta x, that is a value. If I see dx, that is a value, but it is just associated with an infinite amount of slices, and that's infinite slices. Dx is 1 divided by infinity. 10 slices, dx is 1 divided by 10, times a constant, you know what I mean? Because you could have 0 to 2, and you could slice this 10 times, and each slice is going to be 0.2. You know what I mean? And so that's 10 slices. The width of each slice is going to be a constant times 1/10. And the constant here is 2. So, yeah, so don't assume that if I have 10 slices, I'm going to have widths of my slices be 0.1. That's only the case if the thing that you're trying to is between 0 and 1. So if k is, your upper limit minus your lower limit, and you did 10 slices, and k is equal to 1, then your slices would be 0.1. But if the difference between your upper limit and your lower limit, 2 minus 0 is 2, I'm just going to call that k. This would be the equation. This would be the number of slices. So that would go here, I is equal to 1 to 10. That's going to be the number of slices. And then your change in x would be equal to k, 1 divided by that number. Hell yeah. Okay, so this was brutal, but I'm glad I did it. I think I'm ready to figure out how they get the summations and how they do that kind of little it seems tricky, because if you've never done it, never be formally taught how to set up integrals with change in x, and then take the limit as change in x goes to 0, and then get this magical integral sign, where it's just the summation of an infinite number of things, because our slice is dx. Our slice is 1 divided by infinity times that constant k. I'm glad I did that. Alright, hell yeah. 1 divided by infinity multiplied by the upper limit minus the lower limit. Which is, anyway. Alright, hell yeah. Alright, thanks for joining me on this one. We did good. Booyah. Alright, hell yeah. So a viewer wanted me to go over composite areas. Now hopefully this is very fast, but what we do is we really dive into integrating, you know, something that is just 1 by 1. This has dimensions of 1. Its area is 1. And so hell yeah. And so we're going to do composite areas. We're going to find the composite area of this, and that's it. You know what I mean? And I'm going to, instead of putting y up here, I'm going to put a function of x, and then I'm going to have this be x. And check this out. If this is 1, it has a slope of 0. And so this is, I'm just going to use y is equal to mx plus b, or f of x is equal to mx plus b. And I'm going to say it has a slope of 0. And so I'm going to say f of x is 0x, and then the y-intercept is 1. And so now I can see that, hey, my independent variables can be, you know, anything between 0 and 1. And when I input it into this, you know, I'm just multiplying by 0. But it's really difficult to be like y is equal to 1. That's the equation of this. And so in a nutshell, that's why I like to use this. F of x, 1, because I know that this is my independent variable. I think the second you use y, it gets a little confusing. Unless you've always established this as xy, then this actually might be confusing to call this f of x. But hell yeah. But let's set it up. And so we're going to come out here, some distance x, and then set up a dx. And this is going to be our area. And this is an area dA. And so, and then and our limits on this are going to be 0 to 1. So our integral looks like this, integral of 0 to 1 of our function. And just what's the, let's set it up, what's just dA? So dA is equal to, our value, and it's our dA that we chose right here is after choosing this value of x. And so when I choose this value of x, I put that value of x into my function, and I get this as my output, that number up there. Because this is the function that we're looking at, just that part. And we get the value of 1. And that's going to be the height. And then if I make a little... Alright, excuse me, I need to get some water. Alright, hell yeah, we got a new battery in. Oh man, now I see this though. Yeah, that's why they set this up. Is they say I'm going to come out a value of x, and then I'm actually going to put a real width on this, a change in x. And then and then they're going to call this a change well, I don't know. A change in area. I don't think they call it that. Alright, so maybe go back to this. But this little area is going to be the height, which is the function evaluated at x, and then multiplied by this width. This width is dx. Cool. I think that's good enough for me. And so that's one of them. If I wanted to sum all of these strips between 0 and 1, then I would be summing them all. And so I apologize. I don't know that. I just made the long video to actually figure out how to relate this and then make the limit as the change in x goes to 0. But I'm just going to say, hey, this integral is the summation of all of those strips. And so we have the integration of f of x dx. Our function is the integral of 0x plus 1 dx. And that would be the area. This would represent the area under this entire line, but we just want the area under 0 to 1. 0 to 1. So those are our limits. Even if you do this, you can represent this as two integrals. So we would have 0 pops out of the constant, and we would have x dx, 0 to 1. I did this in 2 steps, probably shouldn't have done that. I should just say this is 0 to 1 of 0x dx, so I can FOIL through the dx, and then plus, I don't know if you, I don't think they, I think it's called distribute, but I don't, you can't, yeah, you set up two integrals. That's the appropriate way to say that. If I have this, I can set up the because there's an addition sign here, I can represent this as two separate integrals. I think that's the better way to say it. So we have 1 dx. So that's what we're doing here. This, I can, anytime an integral has a constant, kx dx, the constant can go outside the integration. So that's all I'm doing here. The 0 goes outside. 0 to 1 x dx plus 0 to 1, this 1 can even go outside, dx. And then the integration of this is x 1 plus 1 divided by 1 plus 1. It's a power rule. Put it in the power, maybe see it a little easier. Evaluate it from 0 to 1. But all of that is multiplied by 0. So anything that we do over here goes away. And then this evaluated is x plus a constant evaluated between 0 and 1. And I'm just going to neglect that 1 out there. But hell yeah, there you go. And we're going to evaluate this between 0 and 1, which is taking 1 plus c minus 0 plus c. And so we're going to have 1 plus c minus 0 minus c. So this is 1 plus c minus c. This is 1. And so hell yeah, and that's what we would expect the area of 1. So let's do that same process with this shape. And then finally we'll do it with this shape. Okay, so this is going to be representing the function y is equal to 0.5. This is going to represent the function y is equal to 1. But see how, isn't it more useful to say, hey, this is my output, and this is my input. This is my independent variable x, and I'm going to put it into a function of x. F of x just means I'm going to have something x. That's what it should look like. And even if your function of x is 1, because y is equal to 1, you can still represent that. And so let's represent these. This is going to be f of x is equal to 0x plus 1. And this is going to be f of x is 0x plus 0.5. And I'll put some scales on there. So hell yeah. And so now, if I want to find the area of that curve and then add it to the area of this one, what we didn't is kind of fascinating. So maybe we should go back to this one. Is what we didn't do is establish that this, we're sandwiching something in here. Just because if this is our equation, y is equal to 0x plus 1. And we're taking the integral. And let's say we already know the integral. And it has to be x plus a constant. This is the equation that we get. And so let's say instead of, sometimes your derivative is y prime. Let's say this is y, integral. I don't know how you would actually represent. How do you represent? If you have an equation y is equal to x, and then the integral of y dx is a family of equations, that's where this is just this is representing a bunch of equations. Because and so what does that mean? It means that if this is the equation of a line that has a slope of 1, a slope of 0, the slope is 0, y-intercept of 1, it means that if I have the equation, the integral equation, if this is the family of equations, I can take the derivative of this and get back this original equation. So that's what integrating does. It says that whatever equation that is the integral, if I differentiate this equation with respect to x, I get the original equation. And so I can have this be y is equal to x. I can have it be y is equal to x plus 1, or y is equal to x minus 5. Because if I take the derivative dy dx, and that would be the derivative of x minus 5 dx, and we'll even do this. You know what I mean? Hey, this y just represents the function. This is the same thing as the derivative of f of x dx. And that's useful too. Because if you're taking the derivative of a function where, this term doesn't show up, in there, I don't know, but you can do the chain rule and stuff. Anyway, so hell yeah. And even this, you can separate this. Hey, I see a positive or negative sign. So this is still just the derivative of x dx minus the derivative of 5 dx. And what this says is, and let's talk through what the hell a derivative is. It says, hey, if I'm going to change the independent variable x, and this is the function. This is the things in the function that might change, but after I input that independent variable x. So if I change x from 0 to 1, this value goes from 0 to 1. You know what I mean? And so I would have, on the top, I would have 1 minus 0. On the bottom, I would have 1 minus 0. Same thing, top and bottom. Doesn't mean it's 0. It's 1 divided by 1. So this is 1. Now, I can change x. I'm going to choose x is equal to 0, and then x is equal to 1. That's what I did here. When x is equal to 0, the top is 5. When x is equal to 1, the top is still 5. The number 5 doesn't change. And so this would be 5 minus 5 divided by 1 minus 0. And that's going to be 0 divided by 1, which is 0. And so this goes away, and then you're just left with 1. And so taking the derivative of x minus 5 is just 1. I just, did my complex way, and this video is no longer or shorter. It's no shorter than the addendum after this. This is crazy. So maybe, yeah, this is definitely not a shorter video. But this gets neglected, the fact that when you take an integral, you get a family equation, and the only real aspect is that if you take the derivative of the thing that you found the integral of, I don't know how to, there should be a little symbol here, trying to represent it like this, because this is the derivative. Well, why not this be the integral? Is that if you take the derivative of this equation with respect to the independent variable, then you get the original equation. And so this satisfies, and that satisfies. The only reason why you can find the area under a curve, because if the integral can be way the hell up here, like how is that useful to find the area under this curve between 0 and 1? Because what if I chose this as my function? And might as well do that. So I'm going to choose, so if I start with the function y is equal to 1, which I'm going to say is 0x plus 1, and then this is where they use. This is why they use capital F. Capital F of x means the integral. And now I get that, because I was just like, what the hell? If you go y and this is the derivative, I guess you could do capital Y. That's kind of hard to write though. But yeah, f of x is your integral. And I'm going to say it's x plus 5. That's the one I'm going to use. And so now I'm going to actually 1, 2, 3, 4, 5, and then do this. 0 to 1. That means this value up here is going to be 10. No, it's not. Sorry about that. Scale is way the hell off. So 1 would be right there. That means this value right there is going to be 6, and I'm going to start with a value of 5. And so, so if I have the integral of 0 to 1, f of x dx, and again, why does that work? Because I'm taking this cube, 0 to 1, and I'm finding a position out here, an x position, inserting it into my function, getting a value, which is represented as this height, and then making a small change in x, or just a small change in the width, dx, that represents an infinite number of these things. And that's what this is. That's one of them. So this is the area. This is dA. This is the area of one slice. If I want the area of all the slices between 0 and 1, I then use this integral sign that says there's an infinite number of slices, but I'm going to add all the infinite number of slices that are a width of 1 divided by infinity, maybe, let's say. And, something like that. It has to be a constant, a factor out here that's based on my limits of integration. Because I said if this was 0 to 2 and I had an infinite amount of slices, then I would have an infinite amount of slices. But my slices would be 1 divided by infinity times 2, I think. The width of the slices. Yeah, the width of these slices are, taking the total width, 0 to 1, so that's a width of 1, and then dividing by infinity. The width of these, if I took an infinite amount of slices between 0 and 2, I would have a width of 2. I would have an infinite number of slices, and so each width would be 1 divided by infinity times 2. So 2 divided by infinity, and that's where that k factor maybe comes in. Alright, hell yeah, we tried our best. And, cool. Alright, hell yeah. So we ran out of juice on our SD card, and so we kind of missed a little bit. I started writing, the family of curves that represent the integral. So we chose, x plus 5, but we could have f of x, or we could have f of x minus 1. So that's the other one that I put in here. And then if I evaluate that at 1 and 0, this equation, at 0 it's negative 1, and at 1 it's 0. And so if I take the difference between them, 0 minus negative 1 is 0 plus 1, is that area. And so so that's kind of the usefulness of an integral, of a definite integral. And that's going to be where you have an integral between a and b of a function evaluated, of a function f of x dx. So that's going to be, here's our function f of x, here is our dx slice, and then we're going to sum all those slices between 0 and 1, and that's going to give us the area of this. There's something I was going to talk about. Oh yeah, so this represents a change. It represents a change in area. Yeah, this represents am I saying that right? Yeah, this represents, oh man. Yeah, you're going to get an area. So taking this integral between these two limits gives you the area underneath this curve. And so we can say this gives us the area between these limits of integration. and that area is equal to the integral evaluated at one position minus the integral evaluated at that other position. So it's just really fascinating that these are exactly what's in the book, but it's like if I can't just talk my way through it, then I'll go nuts. But this is exactly where, like, you'll get the gravity equation where you have acceleration is 10 like meters per second squared. And this represents dv dt, and you use separation variables to get dv is equal to 10 dt, and this is a change in velocity, between velocity 2 minus velocity 1, which is the same thing as velocity 2 minus I want to say, velocity, 2 plus dv. That's what this is. That's 10 dt. Oh, that even really spells it out. That's velocity at, position 2 minus the velocity at position 2 plus a change in, and you could say this is the velocity at position 1 minus, no, you wouldn't say it like that. Sorry about that. This would be my... So if you have a position 1, and then you have a position 2, and then your change in position is dv. Oh, shoot. But this would be an equation for velocity evaluated at a position 2 minus an equation for velocity. After you do the integration. That's what I was trying to get at. But before you do the integration, it's literally how we talked about. It's just one slice. So this represents a one slice change in velocity. Oh, but that's the huge thing about integration, where I think representing it by an area is so fascinating, because I think it makes less sense. It makes more sense if you say this is acceleration and this is time, and acceleration is meters per second, and this is time in seconds. And if I have these units and multiply them together, I get meters per second, which is velocity. So if I come over here and take a dt slice and find the area, so this is now 10 dt. Well, heck yeah, this is going to give me but this is a very small slice, and this could be a change in t, or it could be so small that it approaches 0. So what is the area of this slice? Well, maybe that's irrelevant, but if I actually sum them up, then I would get something relevant. I want to know, in the area of this under the curve between 0 and 1 seconds now represents an area of 10 meters per second, which is free fall. Time is equal to 0 to time is equal to 1. This ball is now going to have a velocity of 10 meters per second in the down direction. Oh yeah, and I was on a bike ride I did 3 days of biking, and this is why the whole area under the curve stuff is so, sure, you can find the area of a table, you can find the area of the square, but only if you use does this make no, let's try to make this make sense. And let's grab a freshie. I'm running out of paper, yo. All right, hell yeah. This is why this doesn't make sense. And let's compare these two. So this we said was acceleration. Acceleration is a constant function, it's 10. And this is time. This is time 0 to 1. This area represents, and this is, well, this has units of meters per second per second. I write it like this because this is acceleration, and you can see it's a change in meters per second per second. If I multiply by seconds, I get a change. So I have a change in time, and this was a rate. So it's only when your initial equation is a rate that integration makes any sense. And is that true? I need to think about that. So now I'm going to say that this represents a height. I mean, sure, it's a height of 1 meter maybe. And then I'm going to multiply it by a length in meters. So if I do that, but this isn't a rate of anything. It's just meters. It's not, you know, any... Or let's work forward on this one and then backwards. So if I did have an acceleration equation that was in units of meters per second, and I multiplied it by seconds, I get something tangible and useful. That's this area is in meters per second. Cool. This area represents a change in meters per second because this equation of 10 represents a change in 10 meters per second per a change in 1 second. That's what this 10 represents when it has units of meters per second per second. And this is the area under the curve, and it's represented as a change in meters per second. So when I say what's the area under this curve, it represents the fact that this ball changes from 0 meters per second to 10 meters per second after a time of 1 full second, a change in time of 1 second. This is fascinating because it seems like, oh, we just have a table and we want to know the area. And that's not true. Because when we... Yeah, so this area represents a change in meters. So let's talk about this. That means this area must represent a change in meters squared. This represents a change in velocity. This represents a change in area. So just the area under this curve meant that we changed from area, and that's hard to see. Because where did we start from? Even over here, it's like, well, where did we start from? We don't even know where we started from over here, right? And I'm trying to figure out if this problem has an initial condition. This problem doesn't have an initial condition unless we put it in. This area still represents the change in velocity no matter what. If we throw the ball down at 10 meters per second in the down direction, its initial speed is 10, but it changed due to this area of 10 meters per second. And this is... I did 3 bike rides where it's just like, if you don't overcome this problem in calculus, I think this is the most derailed thing that you can do to yourself in calculus, is say that this is a physical area under the curve, and I'm trying to find that physical area by using integration. Because when you do get this capital F integral, it's a family of equations. It represents x plus a constant. That means it's x plus 1, x minus 1, x plus 5. And its value, and this constant is always typically in an initial condition. An initial condition when x is equal to a known value. So, and then this represents, does the family of equations, does this represent area or change in area? That's kind of what's confusing me. This represents area. If we have an initial condition. And it's because this represents a change in area based on this first equation. So if we start with a table, if I say this is my origin, where if x is 0, I still have a table. That's where I start. It's like the overhead of a building, you know what I mean? It's like costs and stuff like that. But yeah, and then I start from here, and then I make a table that's 1 meter. Well, I'm going to have 1.5, so let's check that out. So if the table that I'm building in this direction is going to be 1 meter, but I already start with a table that's 0.5 by 1, which is 0.5 meters, then my initial condition says when this x value is 0, when I haven't even started building any new table, I'm still left with an area of the old table. And so that's going to be 0.5. And that means that C is 0.5. And then so we have our initial condition that this f of x represents the area of the table as a function of x. And that is going to be x plus 0.5. And if I make a 1 meter table, I'm left, this is my area. Cool. And that's going to be 1 plus 0.5, and that's going to be 1.5. So that's fascinating to me, because this origin point does matter then. So if I do have this square, there's one thing that I overlooked then. F of x is 1, this is x. 0 here is, yeah, there has to be a point where, yeah, that's fascinating. So if I'm saying the area is the area of this table as a function, so I'm going to say area as a function of x. Now this just makes sense from an intuitive perspective. Is there a value of x where this table has no area? It always is going to have a height of 1, but if it's just a strip, you know what I mean, that with, a string, it's not a table, it's just like a dimension of height with no width, then it will have an area of 0. And so for a problem like this, the initial condition is that the area, if x is 0, the area is 0. So if we integrate this, we get x plus c, which represents, see, it seems like this needs to represent the change in area. Maybe it doesn't. It's only the change in area if we have it evaluated at a second point minus a first point. If we take the difference between the second and the first, this is also the area. Well, this represents the change in area. Alright, hell yeah. Let's go back to differentiating this. Because if this area represents a change in meters per second, and then if I differentiate, I'm going to change this velocity as I change the time. That's taking the... So if... If this represents the integral, but it represents the difference between a chosen, if this represents a family of curves, it says, cool, choose one of those families of curves, and then take the difference between the 2 points that you're dealing with, and that's going to yeah, so even though this is a constant and can be adjusted, evaluating at one point and in another and taking the difference between those 2 points is something very tangible, and that gives you the change in this case, the change in meters per second.